Uh, okay, dear friends, today we will listen to Professor Tian Anyuan. He will give this topic two combinatorial problems on the triangular grid and their connections with topology. So let's welcome. Thank you.
Thank you for introduction. Is my voice clear now?
Yes, yes.
Yeah, okay. Maybe I will introduce myself. Uh, First, actually, I'm not a professor. I just graduated from the Shanghai Jiao Tong University under the supervision of Professor Yao Kun Wu. And my first research interest primarily focus on the combinatorics, and I'm also very interested in with this relation with other mathematical fields, including the topology. So today I will introduce two very simple combinatorial problems on the triangle grid. What is a triangular grid? It is just this graph on the right of the screen, and it's a very uh, how to say classical graph in combinatorics. And I will uh, introduce two very simple combinatorial problems on it, just like playing some games on it. And actually, the two combinatorial problem have some background and in uh, some other
I
uh,
apologize
areas of,
apologize for being late.
sorry,
Okay.
okay. Oh, okay, I will continue. Yeah, today I will introduce these two very simple combinatorial problems on the right graphs, and I will introduce how topology is involved in these two problems. And as in my talk will be divided into four parts. And first, I will introduce the first problem, and will give a proof of the in the first problem, and next I will introduce the second problem and introduce the how it is uh, related to the Hermitian sum of squares conjecture, which is a problem in complex variables. So the two problem actually have a same mathematical root, and we will introduce first the combinatorial models, and next we will introduce some backgrounds why we are interested in these combinatorial problems, and finally I will introduce how topological ideas are involved in these problems. So this is basically the mathematical root. Okay, let me get started. So the first part is about a numbering problem in this triangular grid. So first, we consider this standard triangulation of equilateral triangle obtained by dividing each side into k equal segments. So this graph has k square triangular faces and k plus 2 choose 2 vertices, right? And you will ask if we assign distinct integers to the vertices, then how small can the largest difference between the integers assigned to adjacent vertices be? And in other words, you label the 1, 2, 3, 4, 5 on these graphs, and you want to make sure that the difference along these edges, the largest difference is as small as possible. That's the numbering problem. I'll give an example. First is row by row labeling strategy. You can label 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 row by row. And you can find that this is a case where k here equals 3 And when here the largest difference is along this edge, right, is 5 minus 1 is 4. So in this labeling strategy, the largest difference is 4. And also you have many other different ways to labeling these graphs. For example, the zigzag rules. And here the largest difference is along this edge is 1 and 7. So the largest difference is 6. So the question is that what is the best or the optimal strategy for this labeling problem? So first, I will give some languages of graph theory, and we will use this language to restate the problem. So first, what is a graph? A graph actually is very easy. It's a pair of the vertex side and the edge side, where the vertex side today we only consider a finite side, and the edge side here is a set of two element sides of the vertices side, and we call them the edges. And if two element size UV is in edge side, we call them adjacent. So here is an easy example for graphs. So the vertex side is a 5-element side UVWSY, and every line segment represents an edge. So for example, the right segment represents the edge UV, U and W. So this is the graph. And next, I will show that what was the concept of linear layout. If you have a graph and which have n vertices, and a linear layout is a bijection from the vertices side to the side 1 to n. Actually, it's in the previous labeling problem, we use distinct integers, and we can actually assume the labeled integers are the set 1, 2, 3 to n. And you can actually view it just you actually assign each vertices along a line, like the example shown in the left side. So these two pictures are two linear layouts of the previous graph. And the right line here, the UW is here. And we can calculate what is the length of the layout. For example, for the edge U and V, its length is defined as the difference of pi U minus pi V, the absolute value of this. And we can define the bandwidth of this particular layout as the longest edges of them, so that it is edge with the largest length in this linear layout. So it's a very easy definition. And the bandwidth of the graph is the smallest possible value when you where pi is along all this linear layout. So this is the bandwidth of the graph. So you should first give a linear layout and calculate its longest edge, and along this linear layouts, you want to find out which linear layouts can give the minimum longest edge. So far it's clear, right? And so the previous the labeling problem can actually comprehend it as a bandwidth of a specific graph. Tk. So let's define the graph Tk, and so we can view as the triangular grid each vertices as a vector AB3 along 3 vector, which the sum of A and B and C is equal to K. So this is the vertices of the graph Tk. And for each side, we find out that if the L1 norm of x minus y is 2, then it is then xy belongs to the edge side. So here, for example, you can see here you have vertices 3, 1, 1 and 2, 2, 1. If we calculate this x, this is y, then x minus y is 1 minus 1 and 0, right? So its L1 norm is just equal to 2. So there is an edge between them. So actually we so far we only transfer the language to the previous labeling problem to the bandwise of a graph Tk. So we use this notation defined before, the bandwise of this graph to the. So we want to calculate what is the value of it. So and the theorem given by Hochberg, McDiarmid, and Sachs. This says that for every integer k, the bandwidth of the graph Tk is just k plus 1. And you can look from this example to say that when you label row by row, the largest difference, the largest difference is simply 4. So their theorem shows that this kind of strategy is best possible in this labeling problem. So I will give a proof of this theorem in the second section of this part. And first, I will show that why we are consider why the bandwidth problem of the graph is interesting. And I will give some backgrounds and applications of why we study the bandwidth problem. So maybe you may curious of why name is bandwidth is used. It is actually comes from matrix band. So for a real symmetric matrix, we can define the bandwidth is current ordering by the first you look at which entries are non-zero, and you for example is Mij, and so beta m is defined to be the maximum of I minus j of those value of it, and along all of these entries, non-zero entries. So this is its current bandwidth, and its minimum bandwidth is defined to be the bandwidth of P times M times P transport, and where P here runs over all permutation matrices. What it means? It means that you can commute the entries, rows and columns simultaneously to let and you want to that the entries are all close to the diagonal. For example, these two are the same matrix, but you can reorder the rows and columns to make sure all the non-zero entries lines where it is not far from the diagonal. So that is a bandwidth. And so in the 1950s, structural engineers reordered the steel framework matrices so that all the non-zero entries lay within a narrow band, so about the main diagonal. Hence, this is why we call the bandwidth. And it's a bandwidth for matrix, and actually for graph, you can always have a corresponding adjacent matrix. The adjacent matrix for graph G, you can define the adjacent matrix so that it's rows and it is a way by way matrix, and it is for U and V. It takes value 1 if and only if UV H is an age in the graph. So for graph, you can actually define such a matrix, and the bandwidth of the minimal bandwidth of this matrix is actually the bandwidth of the graph. You can see that they actually the same definition for graph and for matrix. Okay, so and next I will introduce another background is about the circuit placement. So imagine that you are an engineer, and in the physical circuit design, we need to align the logical models to a location on a card or board. And there are many connections between this logical module, and you need to use a wire to connect them, right? So if this logical modulo are assigned in a linear card, which means they are aligned linearly, and you don't want to the wire is too long, so you want to make sure that every wire is as small as possible. And for example, Turner uh, says that they actually want to laying out circuits so as to minimize the length of the longest wire. So, uh, you find that if you want to make sure minimize the length of the longest wire, it's actually our bandwidth problem for graphs, because the ways you align them just is a linear layout of the graphs. So so the bandwidth problem for graph is actually has this background for physical application. And I will give another background of this. It is about coding problem between the lunar television image. In 1922, in 1962, sorry, during a summer job at the Jet Propulsion Laboratory, and Larry Harper encountered a coding problem motivated by the transformation of a television image from the moon. And here is some sentence in his reminiscence. And it says that At Posner, my boss, that sum of wonders gave me a number of good problems to work on, but one that proved particularly rewarding was to determine whether or not the coding scheme that was used in transmitting those TV pictures back from the moon could be improved. Here, the pixels that make up the pictures were registered as shades of gray. So there are totally 64 of them from black to white. So you have 64 gray levels, and they were encoded as 6 tuples of zeros and ones for electronic transmission. So occasionally, a mistake would be made in transmitting a symbol. It may change in 0 to 1 or change in 1 to 0. So it will cause a mistake in the shade of gray for that pixel. So the actual change depending on the code you use. So for example, you encode the white one, if you use 0, and include the black one 0, 0, 0, 0, 0, 1. If you maybe I will write down. If you use this code and you include this one, you using this code, but whenever there is a mistake of the last coordinate. For example, if there is maybe some electronic transformation, the 0 is not correct. It may be transformed to 1. So when you get the picture, the white pixel will be changed into black. This is what we don't want to see. So maybe you can encode this black one to be 1, 1, 1, 1, 1, 1. So this is more safe. And if you write down it by the graph theory language, and it is actually a labeling problem on the hypercube. So what is a hypercube? The d-dimensional hypercube is a graph whose vertices is 0, 1 to the power of d, which can be looked at as a set of d tuples of 0, 1 vectors. And then two binary words are adjacent when they differ in exactly 1 coordinates. And the coding question is that if you choose a bijection phi of the vertices side to integer 0, 1 to the d minus 1, and if one bit flips, then how should the phi minimize the resulting gray level error?
What is gray level error?
Actually, we need to we may need to good definition of what is a gray level error, and here is we can give a measure of the gray level error. That is, for example, we can define this parameter. Sorry. Rj of pi. So when you give when you give a linear, first the encoding is actually linear layout, right? And for linear layout, we can define this value Ljrj of pi. It is first you calculate the difference along each edge, and so there are many edges between them, so you need to take the sum of over all uv from the edge side of G. And here there are many different ways to define the how to measure the grade level error. So you can consider the this different definition. And when R is infinity, it is just the it becomes maximum over this edge side, and we calculate the difference of each side and see what is the maximum value. So it's actually the bandwidth of this linear layouts. So for when R is infinity. So actually, maybe this is a general model because we may consider different values of R. When R, for example, when R is 1, actually you are calculating the somewhat total influence of not only one edge, but the summation of the influence, something like that. So for this model, we can ask for fixed G and R, which linear layouts maximize this J of pi. And in particular, if the G is a hypercube we defined before, and how does the optimal coding depend on R? Okay. So that is the answer for hypercube when R is 1, 2, and infinity. So actually, when R is 1 and 2, the optimal labeling is just given by the natural binary order. So natural binary order, you can see this picture, and it just read each binary words, the 0, 1 binary words, as a binary integer, and arrange the values increasingly. So it is just the binary. You can view it as the binary integer and arrange the values increasingly. So this natural binary order. And it is proved that when R is 1 or 2, the natural binary order is the best ordering strategy for the in sense that it minimize the parameter Lj of pi. So this order can have the minimum value of this Lj of pi. And when R is infinity, the optimal labeling becomes the Hales order. You can look at the right picture. And the higher order is defined as following. First, you can group words according to a number of ones. And within each group, you can just take the natural binary order. And you can read them as binary integers and arrange them increasingly. So this is higher orders when on the three-dimensional hypercube. So this is you first you group them here. This group has only 0, 1, 0 ones, and here we have we according to the number of ones there only is 1, and here are 2 ones, and there are 3 ones, and among each group you only use the natural binary order. So this is so-called higher order, and higher order, and also proved by Harper. It is optimal labeling when R is infinity. Okay, So, but actually, when R is not 1, 2, or infinity, there is no answer for this problem. We don't know what is optimal linear layouts. And here is some experience. And I use AI programming, and it tells me when even for the four-dimensional hypercube, and optimal order can have many distinct optimal regimens. For example, we can order the vertices like this. We can write the vertices of four-dimensional hypercube by their binary values, and the two intermediate orders are these two order. And when R is growing from 1 to infinity, it will have a phase transformation phenomenon. The optimal order will transfer from natural binary to A, then to B, and finally to Hills. This is, I think, is very interesting phenomenon. But so far, we don't know what is the um, order for the general dimension for higher dimensional hypercube. And this is many other graphs, and we can and this results on is bandwise. Okay, maybe I introduced many backgrounds and why we study the bandwise, and we can just return to the original problem. It's a numbering problem for the triangular grid. So actually, if you lost the first part, it's okay. We are going to give a proof that the bandwidth of the triangular grid TK is just k plus 1. So maybe we can recall the problem. Now, well, the problem is we want to assign the distinct integers to the vertices and want to know how small can the largest difference between the integers assigned to the adjacent vertices be. And the U direction to prove the bandwidth equals k plus 1 is upper bound, because the row by row labeling we displayed before, and you can easily calculate that this labeling has the largest age difference k plus 1, so it's an easy direction. And now I will give the proof of its bandwidth is just k plus 1 using a topological method. So first, I will give some definition. So we use V1, V2, V3 to reference the three corner vertices of this grid. And we define for each
Excuse me, you are talking about the triangle. Is there a similar problem for the tetrahedron? So if we take a graph coming from dimension 3 in a similar way, we put triangles in layers.
Yes, there's maybe you want to say also a grid for Hesiod, and maybe I haven't seen that this problem is studied for the graph you said, but uh, many actually many graphs of obtained by triangulation is studied. I mean, if there is for example, n-gons, and we take a triangulation of it, and this triangulation will study, I think. But I haven't seen that for maybe tailoring using hexagon. Uh, this type of graph study. Yes, thank you for your question. Maybe let's continue.
Sure.
Okay. For okay, so we define the corner vertices is as V1, V2, V3, and we can define the side the opposite the side opposite Vi by Pi. For example, this is V1, so the P1 is the side of these five vertices. So Pi represents the sides. So this is there is three sides in the triangular grid. And here is an important concept of the connecting side. And we will define that what is a connecting side. A side is called connecting if there is vertices of S, and from which we can reach each of the three sides by passing TK whose vertices all belong to S. For example, this in these in these six right vertices, this six vertices is connecting because it can reach each of the three sides. And actually, if you only use the P1 itself, it's connecting, right? Because this vertices is a intersection of P1 and P3, and this corner vertices is the intersection of P1 and P2. So this P1 actually reach each of the three sides. So P1 itself is intersecting, and it is no hard to prove that every connecting side in the TK has at least k plus 1 vertices. It's no hard to prove. I'll admit this part. And actually, if you use induction, it's very easy to show that a connecting side is at least have this k plus 1 vertices. So this is the definition of the connecting side. And here is a very useful lemma for the connecting sides. It says that if you color every vertices as a black or white, and you consider the side of black vertices and the side of white vertices, then exactly one of the set of black vertices and the set of white vertices is connecting. And I'll say it is a corollary of the Sperner's lemma. So first, you can know how to see that these two vertices, these two set of coloring cannot be both connecting because, for example, you have the one color set is connecting, and let me change the color, and the other set is also connecting. It's impossible because whenever the first color is connecting, it will prevent other vertices from, for example, if the here if the red color here is connecting, and it will lead to the fact that every vertices of this region cannot reach this side, right? So this part is easy. I mean, the two set of the set of black vertices and the white vertices cannot both connecting. So we want to prove that there must be a color size a color set of vertices is connecting. So I will say this is a corollary of Sperner's lemma. Sperner's lemma, I think, is very famous, and it's even one of the most famous results in the combinatorial topology. So I will state it here. So first we label the vertices of this grid by 1 and 2 and 3, and such that in the side of Pi there is no label I. So for example, in this side P1 there is no label 1, and similarly here is no label 2, here is no label 3, and under this labeling rules, and Sperner lemma says that you can always find out triangular face which has vertex labels 1, 2, 3. So this is what Sperner's lemma says. It says that there must be somewhat 1, 2, 3 label triangular face. And next, I will use Sperner's lemma to prove the previous two coloring lemma. So first we can assume for the sake of contradiction that neither the set of black vertices nor the set of white vertices is connecting. And then for vertices V, we define CV to be its monochromatic connecting components. It means that for example here, the black vertices V is connect and these three vertices is in black color. So CV is just a set of these three vertices. And since by the assumption CV is not connecting, right? So it must miss at least one side. So we want to find some contradiction. It must miss at least one side. And we can define lambda as the minimum of I, where the CV, the intersection of CV and the side PI is empty. For example, in this picture, CV is miss the side 3, so lambda V is 3. And maybe CV will miss many different sides, but we only label them using the smallest index. So this is lambda V. So lambda V is actually the you label what is using 1, 2, 3 is what Sperner lemmas the conditions in Sperner lemmas. And actually, we can check that this strategy of the lambda satisfies the assumption or the labeling rules in the Sperner's lemma. This is because that if V is in Pi, so for these edges, then it itself is a element of Pi, so we cannot have lambda of V is I. So therefore, lambda here, this labeling satisfies the Sperner's boundary rule, and the Sperner's lemma will now give an elementary face with labels 1, 2, 3. Right here, we use Sperner's lemma. We get an elementary face with labels 1, 2, and 3.
And so what's how to get our statement? So we have this face with 3 labels, and what then?
Yeah. Then we can find out its contradiction. Why? Because you can assume this is 3 vertices of this 1, 2, 3 label face, and because we only use a bicolor, so at least 2 of them have the same color. For example, U and V have the same color, and they have same color and they are adjacent, so their connecting components are the same. So therefore, their lambda of them must also be the same. So this gives a contradiction because this says that we cannot have labeled 1, 2, 3, and at least 2 of them must be the same. Yeah, so far we derive a contradiction, so it is clear.
Yes, sure.
Okay, thank you. Yeah, now we have finished the proof of the two coloring lemma, and now we use the two coloring lemma to prove the result the bandwise. Yeah, we move to the okay, and first we need some definitions of the size. So now we fix numbering of these vertices 1, 2, 3, 4, 5, 6, 7. And after we numbers 1 to I, we now divide the vertices into 3 regions. The first regions we use yellow color, and it is the vertices we already numbered. And Ri is the unnumbered vertices, which is adjacent to Yi, which means there exists some vertices in Yi have edges in and adjacent to the vertices in Ri. So and Bi, which represents all the remaining vertices. So for example, here, when I is 7, and these 7 vertices is just you have already numbered vertices. And the right part is those vertices adjacent to Yi. And Bi is all the remaining vertices. So this is a definition of Yii and Bi. And observation is that for every I, we have the bandwidth of pi is at least the size of Ri. That's why, because you are numbering this, you are numbering them using 1, 2, 3, 4, and you can see that these vertices in Yi must have distinct labels, and these labels are larger than I, right? If this is because the first I integers is in the set Yi. So in Ri, these labels are larger than I, and they are distinct. So for some elements in Ri, its labeling must is larger than or equal to R plus the size of Ri, and its neighbors in Yi and has label at most I. So there is a large difference between R and its neighbors in Yi. So this is why the bandwidth of this vertex labeling is larger than or equal to the size of Ri. So this is observation, and actually this is why we were divided in of this vertices into these 3 parts. And next, we want to prove that bandwidth is larger than or equal to k plus 1. And actually, we prove that a connecting site must have size at least k plus 1. So it remains only to find an index I for which I is connecting. So now we want to find that find an index I for which I is connecting. Actually, I is very easy to find. We can choose I so that the Yi plus 1 is the first connecting prefix. And here connecting means it is a connecting site. It touches connecting component touches the 3 sides. And so that Yi plus 1 is the first connecting prefix, but Yi is not. And such I must exist because when the I is equal to the number of the vertices, Yi is just all the vertices. So such I must exist. And here we found that we adding the number, if we label the new vertices using R plus 1, from yi to y plus 1, it makes it connecting. So the I plus 1 must lines in the class Ri, right? Because if you the if you label the vertices in the Bi and using R plus 1, it the Bi and the Yi has no edges. So you add if you add R plus 1, it cannot make Yi from not connecting to connecting. So we claim that the number of the vertices we labeled by R plus 1 must lines in Ri. And because YR plus 1 is connecting, we know that Yi and the union of Yi and Ri is connecting. And by the two-color lemma, it is connecting means complementary of it is Bi is not connecting. And again, because Yi and Bi no edge from Yi to Bi, and Bi is not connecting, Y is not connecting. So the union of Yi and Bi is not connecting, right? And then you can use the two-color lemma again to show that the complementary of Yi, the union of Yi and Bi is Ri, is connecting. So this finishes our proof. So we simply choose the I, and so that I is connecting, and so that it's connecting and use the bound before, we can finish the proof. Yeah, so far is it clear? You can interrupt me whenever you want.
For your illustration here,
Yeah.
the R is not connecting, is that right? So in this illustration,
Yeah.
R
Yeah. In this picture, I is not connecting. Yeah, I put it just I want to make sure you know what is Y, I, R, and Bi. Yeah. So in this example, Y is not connecting.
okay.
So I think this proof is very uh, interesting, and they use the two-color lemma twice, and to show that R is connecting. Okay, I'm going to, next I will go into a totally different problem, and I want to make sure that this part is clear. And if you want to have ask some questions, you can ask now. Okay, and here is some reference of this this part. And the next is oh, I have only maybe 30 minutes. Okay, the second part and discuss also a coloring problem on this triangular grid, and I will discuss its relation to sum of squares conjecture. And this part is a joint work with Professor Wu and undergraduate student Peng Zhu. Okay, so again, we use only one page to introduce what the problem is. We consider every downward pointing elementary triangle. So what is downward? So the purple one is a downward triangle, but the red one is a upward triangle. It's just the triangle in this picture have these two position, and actually we think of the sum of sides as a degenerate triangle. For example, we we can consider this is also a downward triangle. But here, one of the vertices lie outside the picture. So this triangle contains only one edge. And for this downward triangle, two vertices lay outside the picture. And so this downward triangle has only one single vertices. It is somewhat degenerate downward triangle. So we will consider this downward triangle and including these degenerate ones. The question is that if we color the vertices by red, blue, and black, and then it needs to satisfy this rule that every downward triangle, if it contains the blue color, it must also contain the red color. So the optimization problem is how few downward triangles can contain red but no blue. So we consider these downward triangles. If it containing blue color, it must also contain red color. But conversely, we want to estimate how many downward triangle they contain red color but no blue color. Yeah, this is our question. You may be very confused with why we are interested in this kind of strange question, and I will introduce later in next. And first, I will give some construction. So here is some examples, and here we color them using red, 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 and blue, blue. And here, this coloring method is not feasible. Why? Because I just mentioned that edge in the boundary is viewed as a degenerate downward triangle. But in this picture, this purple edge containing blue but no red. But our coloring strategy, it requires every downward triangle containing blue, then it must contain red. So this coloring strategy is not feasible. And for the right it is a feasible coloring. And here we have 3 red points and 1 blue point. And you can check that every triangle, downward triangle, if it contains blue, it must contain red color. And there are 5 downward triangles. They contain red but no blue. So the score of this coloring strategy is 5. So we want to make sure this value is as small as possible. But one thing I forgot to mention that in this problem, when there is one additional rule that the blue color cannot be empty. If it is empty, we can choose every blue, red, all these are empty. But in this coloring problem, the blue color vertices cannot be empty. So this is basically the question. And here we also give a general model is for higher dimension. So we write this z greater than equal to 0 to power n s zns to be this set of n tuples of integers, non-negative integers, where their sum is equal to s. And when we study the coloring problem on this side, actually this side have natural connection with the degree vector of some homogeneous polynomials. So this is somewhat why this problem is connecting with complex variables. And here we use EI to denote a vector with 1 in coordinate I and 0 elsewhere. And for vector alpha in this layer, we always call this S layers of the n-dimensional integer vectors. So the S layer vector alpha, you can define its shadow by this size, and it collects those elements where you +1 in some coordinates, right? So it is a shadow of this vector. So its shadow is actually a subset of the S+1 layers. And for a subset of ZNS, you can also define its shadows. And next, we define the parameter PNS. So the PNS is, we want to calculate what is the minimum value of the shadow of X minus the shadow of Y among those X, Y in these layers where the intersection is empty and Y itself is empty side, and the partial Y is a subset of partial X. So this is the parameter PNS, and our question is to determine the PNS. So if you, I want to say that it's just a translation of the language. If you take n equals 3, then this determination of this parameter is just the coloring problem before. And you can check that the X represents red color and Y represents blue color. It's actually a translation of the language. And it also defined for general n, but not only n equals 3. So our task now is to determine the parameter PNS. So yeah, so for this part, I want to translate the language of PNS with the previous coloring problem, but I think I can skip this. And this is the construction of the coloring for P32. And for the best coloring strategy for n equals 3 and s equals 2 is here. These two coloring strategies are both the best. This is when n equals 3 and s equals 2. So for general n and s, and we can construct two coloring strategies which are generalizations of these two examples. So let me define a kind of coloring strategy. It is denoted by Sn, and we define Sn is a pair of X and Y, and it is called S because the set Y contains only one single element. So it is a single element, so we call it a assembly S. And this is Y, and this is X. And you may don't need to read this definition, but only you just imagine that it's a somewhat generalization of this picture, the left picture, to higher dimension. So it is a construction of Sn. And you can calculate that the difference of the shadow, the size of the difference of the shadow can be calculated to be this value. And also we can generalize the right example to be the Bn. So for the Bn, we first partition the side, here it represents the side 1 to n. We first fix a partition, and the blue color we used is just is only 20001 with only two ones, where the location of ones is a bipart graph. It means I is in the first part and J is in the second part. So it looks like we take ones in the first half and takes another ones in the second half. So this is a set of blue color. And we can take X to be the complementary of the Y. And we can calculate that this construction has different shadow like this. Well, maybe that is not so important, but here is a configuration before when here n is equal to 4, and it looks like this. And I only show them, but you don't need to remember what's this definition. But here we compare the size of Sn and Bn. You can find out only for Bn equals 4, then Bn will beat Sn, which means Bn has a smaller size than Sn. And we can prove that the construction of Sn and Bn are actually the best construction. That is, we answer the values, we determine the value of P and S. And here is when equals 4, and not equals 4 is Sn, and when K n is 4, it is 8. So the construction comes from the Bn. So this is our theorem for this coloring problem. And next, I will introduce why we are why we are lead to this somewhat strange coloring problem. It's about the Hermitian sums of squares. And I will introduce why this coloring problem varies from the Hermitian analog of Hilbert's 70s problem. So next I will give some language in the complex variables, and maybe some part is I only want to introduce why we are consider this problem and why we need this theorem to prove something in the sum of squares problem. So first, polynomial is in variable z1, zn, and z1 bar to zn bar. It represents a complex variable, and it is called Hermitian if for some s, non-equal integer s, A can be written as a product of these three metrics, where HA is a some Hermitian matrix, and eta is the row vectors of all monomials in Z1 to Zn of degree at most s. So it is the Hermitian matrix. The other was if you consider, for example, the if you expand this multiplication, you will have somewhat z1, z1, z2, z1, and the coefficient of the here is a c. Sorry, it's a maybe it's It's actually a very easy definition. For example, the coefficient of Z1 and Z2, and it is just a conjugate of the coefficient of Z1 bar, Z2 bar. So and so on for any other coefficients, it's the same. So this is simply the Hermitian matrix. And the matrix HA is called the coefficient matrix of A, and then its rank, the rank of the matrix is defined to be the rank of this polynomial. And it is called the diagonal when it's a coefficient matrix is diagonal, which means that it has a form the alpha norm square times C alpha, where alpha is a degree. And Hermitian polynomial, it is called the sum of square norms, or called SOS polynomial. If this polynomial can be written as a square norm of some holomorphic polynomials, H1 to Hk. If it can be written as the sum of norm squares, it is called a SOS polynomial. And actually, a simple fact is that if it's a sum of squares, then the coefficient matrix is semi-definite, positive semi-definite. And some questions of this area are always asked: what kind of polynomials will be a sum of squares polynomial? And also they asked what is the prolongation of the polynomial is a sum of squares, not only itself, but it is a prolongation of it. So prolongation of the polynomial is simply 8 times this polynomial. And if we put R to be the rank of the prolongation, and we can have the SOS conjecture, which is given by Abfield. It says that if the prolongation of the polynomial is a sum of squares, then the rank of it must satisfy this condition. I will give a explain of this, but the conjecture can be viewed as a quantitative complex variable analog of Hilbert's 17th problem. It's some study of the rank of this polynomial when it can be written as a sum of squares, and one may seek to estimate the sum of SOS rank of an SOS prolongation. So this problem is also in connection with the proper holomorphic mappings between complex balls. And this is what the SOS conjecture predicts. It predicts that if the prolongation is a sum of squares, and then its rank has some gap phenomenon, which means that it can run only in the following intervals. It also means that there are some gaps between the possible values of the ranks. So it is what is SOS conjecture says. And here's some progress on the SOS conjecture. Maybe I'll skip this part of the progress of them. And here is a diagonal weak SOS conjecture, and actually, if we can prove of this conjecture, we can prove the original SOS conjecture, but actually I'll omit this part. And yeah, we give actually prove the weak SOS conjecture in case that the A itself is a diagonal Hermitian polynomial. So we give the diagonal with SOS theorem. It says that it's like this, and it calculates the rank of it is greater than or equal to this value. This value is exactly the optimal coloring parameter Pn. And yeah, using this theorem, we can prove the conjecture of Wang Yue and Zhou and establish the SOS conjecture in the diagonal case. So this is a connection. Y is the coloring problem is related to the diagonal weak SOS problem. So this corresponding between the combinatorial side and the algebraic side. So you can have a look like this. We can transfer the algebraic language into a purely combinatorial language, and so that the diagonal weak SOS problem can be translated to the coloring problem we stated in this section. And here is maybe the final problem is a variant of the PNS. Actually, we all have determined the value of PNS, and we want to seek more such coloring problem which have a natural algebraic background. So we want to find out more such problems in combinatories. And here is another one. We color the entire layers with only two colors, where S is red and Y is blue. And we can define the tailed PNS, which is that here we partition it into two sides X and Y, partition the layer into two sides, and we want to know what is the set difference of the shadow of X and the shadow of Y. So this is the next parameter we want to calculate. And in the coloring language, it is just the number of monochromatic upclicks. And this is some known results for this coloring problem. And here we give new results for the PN tilde 2. And if you are interested, you may go on to estimate for all this PN tilde S. And here is some picture of the some coloring strategies for this coloring problem. And actually, this construction works the best when in the 3 and S is 4. Yeah, I think I have no time to explain to give the proof of the tilde P3S. But I want to say that in this proof of in this coloring of the PN tilde S, there also exists some argument that have some topological favor, and I will share these slides, and I am not going to give the detailed proofs of this. And it is for the tilde P3S, and in the proof of its exact value, we will use some identities and some also I think it's very similar to Sperner's lemma sets, and this kind of argument will help us to give the exact value of the P3 tilde S. Yeah. But there's some reference for second part. And the second, thank you for your attention. That is the end of my talk. Thank you very much.
Okay, thank you very much. Can you please send the slides of your talk? So, dear colleagues, are there any questions or comments comments on this talk? Any more remarks? Okay, if it's not the case, so let's thank the speaker again. The talk is recorded, everything is okay. Thank you.
Thank you.